Hello, in this video we discuss about Taylor approximation and Jacobian matrix. Suppose that you have some function z equal to f x1, x2, and so on xn. Function of n variable. Okay, we know how to find partial derivatives of this function with respect to x1, x2, and xn. Right? Let's say f x1, f x2, and so on fxn. This is nothing but gradient of the function f. This is gradient, okay? And if the function f is complicated, as in calculus 1, we have learned the problem how to approximate a function using the tangent line, right? We also have such problem for function of multiple variables. Before we move to that, let me remind you what we did in calculus 1, right? Suppose that we have some function right here, okay? And we want to approximate this function using the tangent line. Suppose that we are considering the point x0, okay? And the function is very good, which means the function is the first point at x0. That means the function has tangent line, right, at this point. Okay, so the tangent line looks like y minus y0, where y0 is the function value at x0, okay, equal to derivative of this function x0, x minus x0. And we can rewrite this as y equal to f of x0 plus f prime x0, x minus x0. That is the equation of the tangent line right here, okay? And we say, now if we consider the interval around x0, we can approximate the function f of x, right, by the equation of the tangent line. So f of x is similar to fx0 plus fx0, x minus x0. So we just replace the function f of x by a linear function. You see that? That is the whole idea of linear approximation. And now, if we consider a function of multiple variables, we still can do that, right? We want to approximate this function f by a linear function. Let's consider some point x0, capital, that is just x10, x20, and xn0. That is a fixed point, right? And we want to approximate our function by a linear function. So I will use capital letter, just x1, x2, and xn, right? And we have gradient vector at this point x0, so I have gradient of f at x0, okay? Now, naively, if I want to generalize this equation, this approximation to the case of multiple variable, I will have the following one. F of x capital approximately equal to f of x0 plus, instead of the derivative, we use gradient, right? F of x0. Instead of product in here, I will use dot product. Okay, I use dot product because we have vectors. So I have x minus x0. Make sense? X0, gradient x0 are vectors. When you consider dot product, you have some scalar right here, right? And since fx0 is scalar, you have some scalar right here. So basically everything is correct. So this is called the Taylor approximation. Okay, this is Taylor approximation. This is very naive explanation. Okay, but I hope that you can see the connection between the linear approximation for function of one variable and Taylor approximation for function of multiple variables in here. Only the difference is here we use dot product. Make sense? Suppose that we have some function f(x) capital equal to x plus 2y squared x. They ask us to find the Taylor approximation near the point x0 equal to 1, 1. Okay, so of course we need to find partial derivatives. Make sense? In order to find gradient, so I need to find partial derivative f with respect to the x and f with respect to the y, and that is 1 plus 2y squared, and here I have 4yx. Don't forget that when you find partial derivative, you look at other variables as constants, right? So you just apply differentiation rules from calculus 1. Then you may apply this equation, right? Just plug everything into this equation. You have fx equal to f of x0, okay, plus gradient of f at x0 times x minus x0. Here is dot product, right? So you have the following one. F of x0, I just plug 1 into the function, right? So I get, 1 plus 2 times 1 times 1. That is f of x0. Gradient at 1, 1 is equal to 3 and 4, right? Times x minus x0, I will have x minus 1 times y minus 1. Makes sense? And since this is dot product, I will have 2 with 1 is 3 plus 3x minus 1 plus 4 times y minus 1. And you see, this is linear approximation or Taylor approximation of our function at the point 1, 1. Don't forget that. And don't forget, if you consider another point, so you might have another Taylor approximation. Okay? In geometrics engineering, sometimes you have to consider different parameters which are functions of multiple variables. Let's say if you have some z, which is a vector of parameters, z1, z2, and zm, right? And each z is a function of, let's say, z1, x1, x2n, and xn. All functions are function of n variables. Okay. Overall, you may express z as a f of x, right? Where x is n cubed, x1, x2n, and xn. But in this case, you will not have scalar function. You have a vector function. Right? You have vector function. Alright, now how to generalize the idea of linear approximation, means the Taylor approximation for a vector function. But the easiest way to think about that is, if you have a vector function, so you may approximate each term right here, z1, z2, and zm, right? Using their corresponding linear approximations. Make sense? Okay, let me copy that formula for each z, and then when we compile everything together, we'll see the formula of that. So if I have z1 is approximately equal to z1 at x0, okay, plus gradient of z1 at x0 dot product with x minus x0 in here. And I have z2 approximately equal to z2 x0 plus gradient of z2 x0 dot product with x minus x0, and so on. I have zn approximately equal to zn at x0 plus gradient of z n x0 times x minus x0. Okay, so if you write all these functions in a vector form, so you have the following one. Yeah, actually z is equal to z1, z2, z so on zn, right? Let me write in the transpose form so that you know it is easier to write. So I have the following one: z1 x0 plus gradient of z1 x0 times I write delta x. How about that? Where delta x is x minus x0. Okay, and here the second row I have z2 x0 plus gradient of z2 as x0 times delta x, and so on zn x0 plus gradient of zn x0 times delta x. Okay, so you have some vectors in here, but you can break this vector into two vectors. You can write in the form of the sum, right? So the first one is z1 x0, z2 x0, and so on zn x0, right? Plus gradient of z1 x0 times delta x, gradient of z2 x0 times delta x, and so on gradient of zn x0 times delta x. Look at this. The first term is okay, right? The first term is nothing but z x0, because the function z is vector function. Don't forget, z is z1, z2, and so on zn. But we are in the transpose form. That's okay. Makes sense. And then what is this? Look at this. If you write this in the form of matrix product, so this is nothing but gradient of z1 x0, gradient of z2 x0 times so on gradient of zn x0, right, times delta x. Makes sense? So overall, if I explore this, I get exactly the Jacobian of the function. Look at this. What is gradient of z1, right? Gradient of z1 is partial derivative of z1 with respect to the x1. Okay. Next one is partial derivative of z1 with respect to x2, and so on partial derivative of z1 with respect to xn. The second row, partial derivative of z2 with respect to x1 and z2 with respect to x2, and so on z2 with respect to xn, right? And so on. The last one is just for zn, zm. Here we have m. Okay. Yeah, here we consider n function and n variables. Let's change a little bit. Okay, let's change the number n for function here. We just have m functions. So I have zm in here, and then partial derivative of zm with respect to x2, and so on partial derivative of zm with respect to xn. This is the matrix of m by n, where n is the number of parameters, right? And n is the number of variables. Make sense? So, in this case, if you have multiple parameters, you still can find the linear approximation, but you use Jacobian. That's what we did last time in the homework. I give you one problem, like you have two functions z1, z2, but in that problem we have a1, a2, right? And a1, a2 are functions of three variables. And I asked you to find Jacobian of the vector function a1, a2. And now you look at this. Look at it one more time, please. So if you have z is just z1, z2, and so on, zn. That is the Jacobian of z. All right. So overall, my linear approximation looks like z is approximately equal to z0, I mean z at x0, okay, plus Jacobian times delta x. Okay. All right, let's consider the following example. And I suppose that you are familiar to this example, right? You have two control points A and B, okay? And you measure C. And the coordinates of C depends on the angle A in here, the angle B right here, the distance from C to A, and the distance from C to B, okay? And the position of C can be described using these two functions. Okay, they ask us to linearize x and y. Means in this case, the position of C is a function of x and y, and x and y are two functions of four variables. You see, four variables in here. Depends on the distance from AC, from BC, and then angles, you know, A and B in this picture. Make sense? So we need to apply Jacobian. We need to apply the linear approximation or Taylor approximation around this point. Okay? So first we need to find Jacobian of this function. The Jacobian looks like you have to find partial derivative of x with respect to LAC, LBC, A, and B. Make sense? So if you consider like vector, x is LAC, LBC, A, and B. So you would have the following Jacobian. You differentiate the function x with respect to LAC, you get psi of 60 degree minus A over 2. Makes sense? And then you differentiate this function with respect to the LBC right here. So all terms in here do not depend on LBC. The derivative is just equal to psi of 240 degrees minus B over 2. And then you differentiate x with respect to the A, right? With respect to the A. So we have 1A right here. Here we need to use the chain rule. Derivative of psi is cosine, right? But and then you have to multiply with the derivative of the inside function, which is -1. So I have the following one: negative LAC over 2. That is just constant. Cosine of 60 degree minus A. And finally, you need to differentiate x with respect to B, right? You do almost the same thing, but luckily we have plus B in here, so we don't have negative. That is equal to LBC over 2. Derivative of psi is again cosine of 240 degrees plus B. That is the first row of the Jacobian. All partial derivative of the function x. Makes sense? And now we will find partial derivative of the function y with respect to LAC, LBC, A, and B again. So I have derivative of cosine is negative psi, right? I have negative psi, but again I have to differentiate this part. You see, 60 minus A. So this gives me, oh no, we are differentiating with respect to LAC. Sorry, so we are good. That means here I only have cosine of 60 minus A over 2, right? And then we differentiate with respect to LBC right here. So that is cosine of 240 plus B over 2. And then now we differentiate with respect to the a. So we need to care about 60 minus a. Makes sense? So I have the root of cosine is negative side. With the negative will be positive. So I have positive LAC over 2 sine of 60 degree minus a. And finally, I differentiate with respect to b. I get negative LBC over 2 sine of cos 240 degree plus b. Right? Because the root of cosine is negative side. That's why we have negative out there. Alright, so this is the Jacobian of the vector functions x, y. Don't forget that. While we are considering the position of C, right? Which is a vector, okay? Because that is a point. A point is a vector. Don't forget that. So we have Jacobian. Once you have Jacobian, you can write the approximation. Or, you know, they give you the point right here, all values right here. All values right here. You have to plug all those values into the Jacobian to find, you know, just a matrix. Okay, so if you plug everything into this Jacobian, you have the following one. The Jacobian at x0 equal to. You do computation, I just write the result, okay? 0.2496, 0.0534, negative A6, 0.8628, 61.3965. That is the first row. And the second row you have 0.4332, 0.4971, and 50.492, and negative 6.5975. All right, once you have Jacobian, you can apply the equation right here, okay, to find the linear function. So you have the following one. Actually, x, which is x, y, okay, is equal to x0. I have x0 already. Makes sense? And then plus Jacobian at x0. Here I should write approximately equal to times delta x. Okay, so how to write this equation in the matrix form? The first one, x0. What is x0? x0 is the position, right? x, y at the given point right here. Makes sense? So that means you have to plug all this value into the equations of x and y into this. Makes sense? To find x0 and y0. So if you plug everything into that, you have x0 is nothing but 1099.9482, and here we have 1173, 2593. Okay, that is x0. Okay, again, right? How to find x0? In order to find x0, you have to plug all coordinates right here, right? Yes, this is the given point, right? Into the original functions, okay, to find x0, y0. And then you already have Jacobian, which is good. I will not just write jx0. And then what is delta x? Delta x is delta LAC, delta LBC, delta A, delta B, right? That's it. And that is your, if I write in this form, transpose, so everything will be correct. Agree? So, you know, this is really interesting and really important, right? And I see in the textbook of geometry, of the least squares estimation and geometrics data analysis, there are a lot of Jacobians like this, and you have plenty of such problems. This problem is taken from that textbook, okay? And I think we already discussed about application of Taylor approximation sometime in the past. This form is really important. First, you replace a difficult function, in this case, vector function, by a linear function, which is already good. Make sense? So if you have some change in here, in this vector, you just plug that values, right? Those values into this and apply Jacobian to find the position of C right way. Make sense? Without any difficulty. That is the usefulness of Taylor approximation. You look at this, you compare this function, right, with the linear approximation. Of course, the linear approximation is much easier to work with. But finally, I have a homework for you. Again, in this homework, we consider some survey network. We have two control points, A and B, okay? And you measure the distance from C to A and C to B. The distance can be found using the following formula. We know that formula, right? When we study vectors and distance between two vectors. All right, and they ask us to find a Taylor approximation of a vector function, DAC, DBC, okay, at the point 1100 and 1173, 205. Right, so you have a point, you have functions right here. That means from here you can write the vector function. So you can find Jacobian and apply the formula right here to find the linear approximation. Okay, please send the solution to me as soon as possible. Okay, if you have any questions, just feel free to let me know. All right, thank you.